recording and sharing my screen. So today we're going to start looking at right triangles and trigonometry. Just a reminder that the final exam will be Wednesday, December 16th. It will only be available from 8 a.m. to 8 p.m. If that's problematic, you need to talk to me before then. Exam 4 will be right now, tentatively, it's due on Friday, December 11th. We'll see where we are in terms of content at that point as it gets closer towards the end of this week. Homework 8.1 is on systems. That's due on Wednesday. There's also a quiz in there on systems that will also be due on Wednesday. The quiz should be available after class today. Homework 5.1, which is on the angles that we started talking about last class, is that next assignment that will be due a week from today. And also the final day that you can turn in anything in my math lab will be December 14th. So if you're working on back assignments, that'll be the last day that you can submit anything in my labs. After that, any missing assignment will be replaced with a 0. Does anybody have questions on any of that? Or does anybody want to look at any homework questions?
I have a question.
Sure.
Does my math lab grade go into our actual grade?
Yes, if you look in the Blackboard grade book, there is a column for your My Math Lab average. I have to apologize. I think I had promised that over the weekend I would upload those numbers and I haven't yet. But what I'm going to do is not the tests in My Math Lab don't count as part of that average. The quizzes in My Math Lab don't count as part of that average. The only thing that counts as part of that average is going to be your assignments, your homeworks. And I will, after I submit zeros for missing assignments, I will drop the lowest couple, and then I will put that average in the Blackboard grade book. Okay? Any other questions? If not, somebody's got a little bit of background noise going. Appreciate it if you would, if that is the case, silence yourself. And let's get started looking at, from where we left off, the idea of coterminal angles. And coterminal angles are angles in standard position they have the same terminal side. And so then I guess the question becomes, how can that happen? Well, let's look at, and I apologize, this is going to get to be an ugly picture. Let's look at a diagram. Let's look at having our angles in the plane. Let's look at having them in standard position. So this is my initial side. And I want to look at an angle whose measure is, let's say it's positive 120 degrees. Well, couldn't I have gotten to that same place if instead of having positive 120 degrees, I went in the other direction and had negative 240 degrees? And wouldn't those two angles look the same? If the picture was just drawn, you wouldn't know which it was. In last class, we talked about angles possibly being considered not just as that geometric figure, but as a rotation. And so let's say I decided that I wanted to go around completely, which is 360 degrees, and then go another 120. Wouldn't that give me a positive 480 degree angle? And wouldn't that positive 480 degree angle look the same as my original 120 degree angle, look the same as my negative 240 degree angle? And then we could also have taken that same set it in the same standard position and gone negative direction and gone a complete rotation, negative 360, and then another 240, which would have given us negative 600 degrees. And wouldn't it have given me that same terminal side? And so depending on how many times I want to spin around, I could have an infinite number of angles that end at that same spot. What they all have in common, though, is if I have coterminal angles.
I'm sorry, I came in late. My internet hasn't really been working that great today.
Okay, was that Jenna?
Yeah.
Yeah, I saw you come in, and that's why I was tripping over my tongue for a minute. I was trying to add you.
Okay, thank you.
Coterminal angles differ in measurement by 360 degrees, or multiple of 360 degrees. Or 360 degrees would be 2 pi radians, or a multiple of 2 pi radians. And so usually, if I look back to those 4 angles that all ended in the same place, am I correct in assuming that people would much prefer to refer to it as that 120 degree angles over the negative 240 or the negative 600, or even for that matter, the positive 480? And so usually we express angles in terms of the least positive or the smallest positive coterminal angle. To do that, we add, if it's a negative, or subtract, if it's a positive. 360 degrees, or 2 pi radians, so let's say, for example, I have negative 735 degrees, and I want the least positive coterminal angle. Because this is negative, I'm going to add 360 degrees until I get a positive. So I'll add 360 degrees. That'll leave me with negative 375. Since it's still negative, I'll add another 360. That'll leave me with negative 15 degrees. Since it's still negative, I'll add another 360, and that'll take me to 345 degrees. And so this will be my least positive coterminal angle. Instead, let's say I start with 1,000-degree angles. This time, because it's larger than 360, we'll subtract 360 until we get something less than or equal to the 360 degrees. So first time I subtract 360, I'll get 640, which is still too big. So I'll subtract another 360, and that gives me 280 degrees. And since it's less than 360, this would be my least positive coterminal angle. And that's in degree measurement. We also have to be able to use that line of reasoning in radian measure. So let's look at another example. Let's look at 17 pi over 6. Now, in order to look at these, I'm just looking at the numeric coefficient on pi. And does everybody recognize that 17 over 6 is greater than 2 pi? So I'm going to subtract 2 pi. So I'm going to take 17 pi over 6 and subtract 2 pi. If you're using a calculator, you're going to just take the 17/6 minus 2. Doing it by hand, though, I'm going to get that common denominator of 6. And so 2 would be 12/6 pi. And I get 5 over 6, which is smaller than 2. So this would be my least positive coterminal angle. And one more. Let's say I'm starting with a negative radian measure, negative 9 pi over 8. Since it's negative, I'm going to add 2 pi until I get a positive. And again, I'm going to go old school and get a common denominator to add. Common denominator would be 8. 8 times 2 is 16. So that gives me 16 pi over 8. And so that sum gives me 7 pi over 8. And this then would be my least positive coterminal angle. Those are right. And that idea of coterminal angles. If so, there's another type of problem that's probably easier to solve using radians than degrees. And so I'm going to look at one more example. Let's say we want to find the distance that the tip of the second hand of a clock moves in 40 seconds if the length of the hand is 4 inches. And so I'm going to try to draw my clock. And so this is my second hand. And let's see, all the way around would be a minute or 60 seconds. So if I'm going 40 seconds, I'm going through this fraction of a rotation, and I'm looking at the distance that the tip of that clock moves, that hand moves. So I'm looking to find this measurement. Well, in order to find that measurement, it's an arc. So I'm going to use my arc length, S equals R theta. R, we said, is our radius, which here would be the length of my clock hand, or 4 inches. Theta is the radian measure of the angle. In order to do that, we're going to have to do a little bit of proportional reasoning. 40 seconds, well, that would be 40/60th of a full rotation all the way around. So let's see, 40 over 60, I guess, if you want to, you could leave that. I'm going to reduce that to 2/3 of tells me the time, multiply. And then my full rotation, the complete circle, is 2 pi radians. And so that's going to give me 4 pi over 3 radians for my angle. And so substituting into S equals R theta, it would be 4 times 4 pi over 3, which would be 16 pi over 3 inches. And if I wanted to, let's say, the nearest 1/10 of an inch, I'm going to take my calculator and I'm going to take 16 times pi, using the pi key, and then divide that by 3. And so it would be, this turns out to be 16.8 inches. How's that one? So is everybody comfortable with our radian measure that we discussed last class, and with our idea of coterminal angles and arc length? Okay, great. If that's all right, then what I'd like to do next is look at right triangles. And a right triangle is going to be a triangle that contains a right angle or a 90-degree angle. If I look at a right triangle, you can't go on the assumption that that's a right angle. You would have the little block in the corner means that it's a right angle. If that's not there, unless the words tell you you have a right angle, you can't assume that it is right. When I look at a right triangle, can anybody remember the name for the side opposite the right angle? Does the word hypotenuse sound familiar? And then the sides that form the right angle are called the legs. And so it has two legs, one leg, two legs. When we look at not just a right triangle, but triangles in general, there's a naming convention, I call it. For triangles. They're named with their vertices, which are uppercase letters. So I could have over here a right triangle, and I'm going to call it CAT. The angles can be named with a single letter. At its vertex. So we'll have angle C, angle A, and angle T. And I'm going to go on the assumption that that's common knowledge. What I'm not sure is common knowledge is that the opposite sides are named with the lowercase letters. So over here, if this is angle A, uppercase A, that side opposite will be referred to as side lowercase a. If this is angle C, the side opposite would be named with a lowercase c. And if this is angle T, the side opposite it will be named with a lowercase t. And so let's say I have another triangle. And let's say this is triangle BAD. If this is angle B, this would be side little b. If this is angle A, across from it would be side lowercase a. And if this is angle D, across from it will be side lowercase d.
Can you hold on a second so I write this down?
Sure.
Thank you.
Is this way of naming the opposite sides with the lowercase letter something that's familiar to you or not? Let me know when you're ready to move on. It's letting me move the chat box.
You're all set.
So then another thing that we need to know about triangles is the sum of the angles of any triangle is, does anybody remember the degree measure for the sum of the angles of any triangle?
180.
180 degrees. And so let's say I have two right triangles. And so the first one will be bigger. And I'll call this triangle A, B, C, right angle at C. And the next one, I'm going to make it a little bit smaller. And I'll call this X, Y, Z, right angle at Z. So since they're right, I know that the measure of angle C is equal to the measure of angle Z. Let's say that we're also given that the measure of angle B is equal to the measure of angle Y. So that those two angles are also equal. What can we say about angle A and angle X? Well, if these three add to 180 and these three add to 180, if two are the same, wouldn't the other angles have to be equal because the sum is 180? And therefore, if two right triangles have acute angles and a pair of acute angles with equal measures, it means that all the angles are equal, that all the corresponding angles and it means that makes the triangles similar. Which means that their sides are in proportion. When I talk about similar triangles, they have the same shape. They don't have to be the same size, but they can be. So they're not necessarily the same size. And so the sides are in proportion. And so it means that the ratios of the sides are the same. And that's going to be true of any two right triangles that have a congruent acute angle. And what happens is those ratios are so useful, those are given names. And we say that the trigonometric functions of an acute angle are the ratio of the sides in a right triangle with that given acute angle. And today we're going to look at those ratios and define them. But any right triangle with a given acute angle measure will always have the same ratio of those corresponding sides. Everybody all right if I turn the page, or do I need to wait a minute? So let's define the trig ratios as the function of an acute angle. Theta. And so we're going to define it in terms of a general acute angle, and then in terms of one particular right triangle. So let's say we have right triangle A, B, C. Angle C is right. So angle A and angle B are acute. The hypotenuse would be labeled lowercase c. The leg opposite angle A would be lowercase a. The leg opposite angle B would be lowercase b. The first function that we're going to define is the sine of theta, which is, again, theta can be any acute angle. And mathematicians are intrinsically lazy and don't like to write. So we have an abbreviation for sine. It's abbreviated SIN, theta. And what it is it's the ratio of the opposite leg to the hypotenuse. Or some people look at it as O over H. So over here, if I look for this in my diagram, the sine of angle A, opposite angle A is little a, and the hypotenuse is C. But I could also refer to the sine of angle B. And if I look for the sine of angle B, opposite angle B would be little b, and the hypotenuse would be c. And so which is considered the opposite leg depends on the angle that you're using for your reference. Next function we're going to look at is the cosine of theta. Cosine is abbreviated COS, and that's the ratio of the adjacent leg to the hypotenuse. And some people look at that as A over H. And so going back to the triangle given, if I want to find the cosine of angle A, over here, this is angle A. Adjacent means next to. So I want the leg that's next to angle A, which is little b, and the hypotenuse will still be C. Likewise, if I want the cosine of angle B, well, the leg that's next to angle B, looking at my diagram, is little a, and the hypotenuse is C. The next ratio that we look at as a function of the angle is the tangent of theta. Tangent is abbreviated TAN, and that's the ratio of the legs. It's the ratio of the opposite leg to the adjacent leg, or people abbreviate it as O over A. And so in my generic right triangle, if I look for the tangent of angle A, well, opposite angle A is little a, and adjacent to or next to angle A is little b. And so that would be A over B. Instead, if I wanted to use angle B as my reference point, the tangent of angle B, well, opposite angle B is little b. Next to angle B is little a. The adjacent would be little a. And so I get the tangent of B is B over A. Have you folks seen this much of trig before? The ratios of the sides. For these, does anybody have a memory aid? I learned if you put them in order, sine, cosine, and tangent, I learned a silly sentence, which was Oscar had a heap of apples, which gives me that the sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Has anybody ever heard of Oscar has a heap of apples? I've also heard it, which probably isn't a good way of saying it, that Oscar had a hit of acid. Does anybody have another way of remembering those? I know there's a made-up Indian name. Are any of you folks Sokotoa? I was never real good with that one because I can't spell real words correctly, let alone made up names. But I think it's so Toa. Does that look familiar to anybody? And so those are 3 of your trigonometric functions.
Can you hold on a second? My internet cut out and I lost you.
Everybody all right with those 3? Have you folks seen those 3 before? Nobody's going to answer me. Oh dear. Are you folks familiar with the idea that there are not just 3 trigonometric functions, but there are actually 6?
Yes.
And there are 3 more of them. And so the next one would be the cotangent. And cotangent is abbreviated COT. And we need an angle. They have no meaning if I don't put that angle in there. And that's the ratio of the adjacent leg to the opposite leg, or adjacent over opposite. And so the cotangent of angle A, going back up to my diagram, for angle A, adjacent over opposite, would be B over A. And the cotangent of angle B, looking back to my diagram, from angle B, adjacent over opposite, would be little a over b. The next is the secant of my angle theta, and that's abbreviated as SEC theta. And the secant is the ratio of the hypotenuse to the adjacent leg, or h over a. And so the secant of angle A, if I look at the ratio of from angle A, the hypotenuse to the adjacent, it would be C over B. And the secant of angle B would be C over A. And then the last one is the cosecant, which is abbreviated CSC. And that's the ratio of the hypotenuse to the opposite leg, or H over O. And so cosecant A would be my hypotenuse, C, over my opposite leg, A. And cosecant B would be my hypotenuse, C, over my opposite leg, B. And if you look at them, tangent and cotangent are reciprocals. Tangent and cotangent are reciprocals. We can say that tangent is the reciprocal of cotangent, or we can say that cotangent is the reciprocal of tangent. And if you look back like when we were talking about reciprocals of fractions, reciprocals of slopes, we said that we flipped them. And so tangent flipped is cotangent. In the same way, we can say that secant is the reciprocal of cosecant. I'm sorry, secant is the reciprocal of cosine. And so the secant of theta is the reciprocal of the cosine of theta, or the cosine of an angle is the reciprocal of the secant of the angle. And lastly, cosecant is hypotenuse over opposite. And if we flipped that, we'd have opposite over hypotenuse, which is sine. So we say that cosecant theta and sine theta are reciprocals, or cosecant theta is the reciprocal of sine theta, or sine theta is the reciprocal of cosecant theta. And those folks, let me shrink it down to one page for a second, are the whoa, didn't mean to do that, are the definitions of your 6 basic trigonometric functions. And so we should be able to, given a right triangle, find the value of each of those. Does everybody have their definitions written?
Can you hold on a second? I'm almost done. I have like a few left.
Sure. Got them?
I got them. I'm good.
Okay. And so one type of problem that you might see is like, let's say, triangle X, Y, Z. Let's say angle Z is right. We know that little x has length 5. We know that little z has length 13. And I want to find all 6 functions of, let's say, angle y. What I would do first is draw a right triangle. Z is the right angle. In terms of the other 2, it's arbitrary which you label X or which you label Y. Once we've got that done, though, the side opposite angle X would be the side that's 5. The side opposite angle Z would be the side that's 13. We want to find the 6 functions of y. So we want to find the sine of y, the cosine of y, the tangent of y, the cotangent of y, the secant of y, and the cosecant of y. Well, sine is opposite over hypotenuse, And if we're looking from angle Y, oh crap, I don't know the opposite side. Can anybody remember how to find the missing side of a right triangle?
We use the a squared plus b squared equals c squared formula.
So to find the missing side, we'll use, it's called the Pythagorean theorem. Which is that a squared plus b squared equals c squared. And it's important here that c is the hypotenuse and that a and b are my legs. And so in terms of the right triangle we're working with, my legs are x and y, x squared plus y squared, and my hypotenuse is z. So that would give me 5 squared plus y squared equals 13 squared, or 25 plus y squared is 169. Subtracting, I get y squared is 144. And so y would be the square root of that, or 12. Because it's the length of a side, we'll only consider the positive root. We won't look at negative lengths until, probably not until you get into, at the earliest, our advanced algebra and trig class, that math 111, or pre-calc. So now we know that y is 12. We can label that other side. And so sine opposite over hypotenuse would be 12/13. Cosine adjacent over hypotenuse would be 5/13. And tangent is opposite over adjacent would give me 12/5. Cotangent is the reciprocal of tangent, so that's 5/12. Secant is the reciprocal of cosecant, so that's 13/5. And cosecant is the reciprocal of sine, so that's 13/12. So use your SOHCAHTOA or Oscar to get your first three. And then remember who are your reciprocals. So, if that looks all right to everybody, let's try another one. Let's say I have another example, triangle ABC. Angle C is right. Let's say that I know little a is 2, little c is 3, and I want to find all 6 functions of angle A. Again, let's start by drawing our right triangle, right angle at C. And again, in terms of which you label A or which you label B, that's a matter of personal preference. But you need to be consistent once you've done that. If this is angle A, opposite side A is 2. If this is angle C, opposite side C is 3. And if we want all 6 functions of angle A, we need to find little b. And if you're not told otherwise, you want it in simplest radical form. And so I'm going to shut up for a minute and ask you folks to use your Pythagorean theorem to tell me what you get for little b. Anybody get an answer yet? Square root of 5? I'm liking it. Did everybody else also get radical 5? Or do we need to work it out? 2 squared plus b squared equals 3 squared would take us to that b is radical 5. And so now using those, we want to first find the sine of a. Sine is opposite over hypotenuse, 2/3. Cosine of a would be adjacent over hypotenuse, radical 5 over 3. Tangent is opposite over adjacent, which would be 2 over radical 5. Oh dear. We can't leave that radical in the denominator if we're looking for things in simplest radical form. So we have to remember how to rationalize the denominator. And so here we'd multiply both numerator and denominator by radical 5 and get 2 radical 5 over 5. Cotangent is the reciprocal of tangent. And here I'm going to let you guys know I'm a little lazy. I'm going to take the reciprocal of the original way we wrote it before we rationalized to get radical 5 over 2. Secant is the reciprocal of cosine. So that's going to be 3 over radical 5. But again, I have to rationalize that one to get 3 radical 5 over 5. And then cosecant is the reciprocal of sine, which, well, we can turn that upside down without worrying about a radical in the denominator, gives me 3/2. And given a right triangle, how is this? Does this look like something that you folks can do? Find the missing side if need, and then find all of the functions of either angle. Hearing no questions or complaints. You guys aren't helping me at all here. Is this okay?
It's fine.
Okay, hearing no complaints, then there are some special angles. And eventually, you're expected to know the functions of these angles. So let's see if we can get through at least one of them, if not all 3 of them today. The first special angle is going to be 45 degrees. And could somebody take the time, please, to turn that into radians for me? Remembering that to change degrees into radians, we're going to multiply it by pi over 180. And so when I simplify that, I get 45 pi over 180, which reduces to pi over 4, not 4 over pi over 4. And so if I look at a right triangle with a 45-degree angle, if one of these acute angles is 45 degrees, and the triangle has to add up to 180, it will turn out that the other one is 45 degrees. And if those two angles are the same, this turns out to be an isosceles right triangle, which means that the legs are congruent. And in order to find the ratio of the sides, I can use any isosceles right triangle, because we said that as long as it's got that 45-degree angle in the right triangle, the side ratio should be the same. And so to come up with these ratios, I like small numbers. So I'll say that my legs are 1. And so if my legs have length 1, how long would my hypotenuse be? If I use my a squared plus b squared equals c squared, that would give me 1 squared plus 1 squared is c squared, or 2 is c squared, giving me c is the square root of 2. And so now, using that, if I want to find the sine of 45 degrees, sine is opposite over hypotenuse, would give me 1 over radical 2, that I'd have to rationalize to get radical 2 over 2. If I want the cosine of 45 degrees, well, the adjacent side will also be 1. So that will also rationalize to radical 2 over 2. And if I want the tangent of 45 degrees, tangent is the ratio of the legs opposite over adjacent. So that gives me 1 over 1, which is just 1. Then for my others, my reciprocals, if I look for the cotangent of 45 degrees, the reciprocal of 1 is 1. If I look for the secant of 45 degrees, the reciprocal of 1 over radical 2 would be radical 2 over 1, which is just 2. And the cosecant of 45 degrees would also be that same reciprocal, which would also give me radical 2. And again, this is in degree measure. We could also look at this in radian measure. And so, for example, if I asked for the tangent of pi over 4 radians, well, pi over 4 radians is equivalent to 45 degrees. So that would also equal that whole number 1. when you move on past this course, you're expected to know these values. I do believe that in my math lab, when they ask you to find them, they draw the triangles for you. Next that we're going to look at is 60 degrees and a 60-degree angle. If I multiply it by pi over 180, would give me pi over 3 radians.
Hey, I have to leave. I'm at work. Is it okay if I leave 5 minutes early?
Oh, sure.
All
The
right.
class is recorded, the notes are saved.
Okay, thank you.
And so when I think of a 60-degree angle, I think of an equilateral triangle. In my equilateral triangle, each of the angles are 60. And so I'm going to make each of the sides have a length of 2. And then if I drop a perpendicular, each of these angles would be 30 degrees. And each of these sides would have length 1. And so we're going to focus on this little right triangle, which has one leg 1, the hypotenuse 2. I'm going to erase this other leg being 2 so that we don't get it confused. And for the other leg, if I use my a squared plus b squared equals c squared, I'd get 1 squared plus b squared is 2 squared. And I would end up with that other leg being the square root of 3. And so now I can use that red triangle to find my functions of 60 degrees. So the sine of 60 degrees, well, sine is opposite over hypotenuse, radical 3 over 2. The cosine of 60 degrees, well, cosine is adjacent over hypotenuse, would be a half. The tangent of 60 degrees, well, tangent is opposite over adjacent, would be radical 3 over 1, which is just radical 3. Cotangent of 60 degrees would be the reciprocal of that, 1 over radical 3. And when I rationalize, it'll give me radical 3 over 3. Secant of 60 is the reciprocal of cosine, so that would be 2. And cosecant of 60 is the reciprocal of sine, so that would give me 2 over radical 3. And when I rationalize, I'll get 2 radical 3 over 3. And there's one more angle that you're expected to be familiar with besides that 45 degrees and that 60 degrees. And the other angle is 30 degrees, which would be pi over 6 radians. And does everybody see that that 30 degrees would be the other angle in the triangle we just formed? And so sine of 30, opposite over hypotenuse, is a half. cosine of 30, well, if I'm looking for my 30-degree angle, adjacent over hypotenuse is radical 3 over 2. And tangent of 30, opposite over adjacent, would be 1 over radical 3, which would rationalize to radical 3 over 3. Cotangent is the reciprocal of tangent. Taking the reciprocal would give me radical 3 over 1. Secant of 30 would be the reciprocal of cosine, giving me 2 over radical 3. That'll rationalize to 2 radical 3 over 3. And cosecant of 30 is the reciprocal of sine, and the reciprocal of a half is 2. So, how cool is all of that? And these would be the exact values for these angles. The exact values, when you're asked for the exact value, you're going to want to use it in radical form and not a decimal. So, and I'm looking at the clock, and it's about that time. So, does everybody have this down? I'm going to stop sharing.